Hello, my name's Josh, and I am making this review video for Chapter 3, just about the atom. So here we go. So what is an atom? I mean, throughout history, there's a lot of different, ideas of what an atom may be. But John Dalton started out, this man right here with the cool glasses, he thought that they were kind of like billiard balls with hooks. They just kind of bounce around randomly, hook onto each other randomly. But throughout time, like he kind of thought they looked like this, just plain billiard balls with those hooks. But going into the late 1800s, research showed that atoms can actually be, divided from one another. They can connect differently, and that there's different forces within them. So Coulomb's law of electrostatic interactions explains how these particles interact, how they separate, how they come together. And it's this equation right here. So the strength of interaction depends on the magnitude of charges and the distance between the two charges. The closer the atoms are together, the stronger they'll be. And especially if they're both strong in their charges and close together, then the attraction between the two will be extremely strong. And so that's really important while looking into how molecules may be the strongest and how they interact with each other, which this really is cool because it leads to the whole entire rest of our class, from kinetic molecular theory to intermolecular forces on molecules. It's really interesting. There's just some little animation there. So then people started experimenting, saying, hey, like, what is it like? So J.J. Thomson set up this cathode ray tube. Right here, you have the cathode, the anode, you have this battery going through, and pretty much as he had two of these magnets, and he'd send these molecules through. And he noticed, he's like, whoa, this is so weird. They always went towards this positive magnet, which means that the molecules that I was sending through, or the parts of the atom, must be negative. Up here, they go that way. Up here, they go down that way. And of course, they were super small, so you had to have this phosphorescent coating, and so it'd leave a little spot there. And then that led to the discovery of the electron. And so in 1897, J.J. Thomson discovered the electrons through this method. He said, okay, wow, there must be a negative source, a negative element to these atoms. It's not just like what John Dalton thought with billiard balls. It's more than that. It has a negative aspect to it. And so that really became because of this. And the magnetic fields is a charge to mass ratio he started realizing. So from that, he's like, okay, it pulls it up this much, it moves it this much. That is a direct correlation to how big this particle is. But the problem was, I mean, as we know now, with modern science, electrons are so tiny. So that was a little problem there. But it demonstrated those all right. So now, we had that charge to mass ratio, but the problem was, we're like, okay, of course we can't see these particles. How big are they? What is the mass of them? So in 1910, there was a MILLIKAN oil drop experiment with Robert MILLIKAN and Harvey Fletcher, which he graduated from BYU. And he was, I believe, a professor here at BYU, which is pretty cool. And so what they do is they had this this container here. You have the x-rays going through, you have the sprayer spraying out oil drops. They go down into a positively charged plate, and then there's a microscope looking in. There's a negatively charged plate with X-rays going through the center of the beam, and there's a small hole letting these oil droplets or these electrons through. Now, how they calculated the mass was they looked at where those electrons sat between the positively charged plate and the negatively charged plate. Because if it was just normal oil, it would just drop and hit the bottom. And I mean, by normal oil, I mean their perception of oil. But now we know there's so much going on inside the molecular composition of oil. But they notice, oh wow, these tiny particles are like floating in between the plates. So they could look in their little microscope, see that. They looked at the mass to charge ratio. They looked at like how heavy the oil was, how much it was floating, how much there was of it, and they calculated, okay, that is how much an electron weighs, which is crazy. And so there's an X-ray going through. I'm not sure if this will work. Boom. Those get sprayed. They go down to the hole. They look at it. They're floating in the air. Positive, negative charge. And then if you're looking through the scope, they fall. And then they're like, there's gravity, but then an arrow here, it should show, is there's also the positively charged plate. And these particles were floating. I just love this. I'll keep going on about it forever. Then F equals QE, of course. And then also, I forgot to mention, when the electric field was minimized, they were able to maximize it, minimize it. When it was lowered, the drops would fall more. And when it was strengthened and made bigger, they'd go up closer to the plate, which is pretty cool. There's intense animation. And there's a set and the known. So through the QE and also through the milligrams, which they knew exactly, they figured it out. Density and volume. Now, electron charge, okay, so they noticed that the charge on Harvey's oil droplets were about these values, which if you look at it, you're like, wow, those are tiny. And then they noticed that the increases by negative 1.6 times 10 to the 19th was the charge of one electron, because they noticed it went up that amount every time the more that they put in. And so that means that each electron added that much charge to the mix. And through that, they were able to find the size, the weight, the charge, all those things, which is awesome. But then a question started to happen. They're like, okay, wow. So we're shooting through these like negative particles, but the problem is we really want to find the positive side. And so they're like, is there a positive side of the atom? And that is where these people came in. Of course, you have Wilhelm Röntgen, you have Henry Becquerel. Sorry, I'm bad with pronouncing names, and Marie Curie, which we all know. So Wilhelm, in 1895, literally 1895, he discovered X-rays, these rays, and with that, Henry Becquerel was able to, and these individuals were able to do this first on the left, X-ray. And then that led, for Henry to do that, he used uranium, which of course emits X-rays, but it is a very dangerous, decaying radioactive substance. So Marie Curie, she studied uranium. She came right after Henry. She said, this is very interesting. She said parts of an atom have positive charge. She used that to determine that they have positive charge. And she described 3 types of radiation. There she is. And so the types of radiation, let's see if this works. So there was a radioactive ore sample, and she would shoot out particles. Alpha particles are positively charged and large. And so they would just, boom, go straight up towards that negative charge prong on the voltage generator. Beta particles are negatively charged and small. And so then they go down to the positive side. Gamma rays are high energy radiation. It's just straight radiation. As you see, it's in the form of wave. It just goes straight through. So from this, she didn't necessarily know, okay, like protons are this big, or protons are like have this much charge, but she knew, in some ways she could calculate the charge, but she really knew that they had both positive and negative subatomic particles, not just electrons that were previously discovered in the Millikan experiment. And so then just by doing some math, they were able to start figuring that out. But then people started thinking, okay, how is this atom, this mysterious atom? Okay, so before we thought that the atom was the smallest you could get to. It comes from, ancient, I believe, Greek and Latin words where it's just like, this is the smallest particle that anything can break down to. But now we're starting to learn, okay, this is crazy. We can break down the atom even further. And so then 1904, J.J. Thomson, he's back. He's spitting science again. And he's like, okay, it's like plum pudding, which you see is here. It randomly has the plum stuff in it. It randomly has other fruit in it. So it kind of looks like this. It's like a positively charged blob with negative electrons within it. And they just kind of like do what they do. And so that's what his model stated and suggested. But as we learn over here, and even this isn't super fully correct, but well, this one isn't. This one is more like it. We know now that, okay, there's protons and neutrons in the center with electrons not rotating like this, but more like this with the orbitals. And so how do we get to that? So in 1911, Ernest Rutherford discovered the nucleus, which, I mean, this begins to be the key to, okay, how are they formed? And so what he did is he had this huge fluorescent screen, and he had the ray emitter, and it would shoot beams of particles forward and hit thin gold foil. So undeflected particles passing straight through hit the other side. But then there was all these particles just hitting all these sides. And so the fluorescent screen just lit up with these marks. And so he's like, oh, what? I mean, like, what is happening? Because he expected it with the current plum pudding model to just go straight through, because, I mean, he's emitting the small particles, the electrons are small, it's just a positive force inside, what's going to happen, So here's what happened. So here's what he expected from the plum pudding model. There's this blob of positive energy, and there's these electrons. And so he expected, of course, some of these particles to go through and slightly hit electron or slightly be curved, but then all be on the other side. Maybe they're not like in a straight beam, but just kind of like a splattering on the other side. But the crazy thing is, we know it's not just a blob of positive energy. We know that it's a diffused electron cloud. And so there are these electrons within the cloud, or the orbital, as we know now in our class. But a lot of his particles would come forward, hit this super, this center nucleus that was a very large mass and substance, and then just go off randomly. It couldn't pass through, it couldn't go around. It was too thick and too big. And so positively charged center contains most of the mass. But it's about 1/10,000th size of the atom. And so he was shocked by this, you know. Like, this is a cool thing about science. It just keeps changing. And he noticed that, okay, wow, this tiny little center, this tiny little nucleus has most of the mass, has most of the weight. And so the neutron and the proton came into being. So the problem was the elemental mass did not equal the number of protons. And elemental mass changes more than 1 AMU between elements. And carbon sometimes weighs 12 AMU and sometimes 13 AMU. They change. He's like, what's that about? And so in 1920, he decided that there must be an uncharged particle. And in 1932, James Chadwick discovers that there is a particle called a neutron. And of course, before that, 1920, about the same time, Rutherford says there's a particle with mass equals hydrogen atom charge equal but opposite to electron, and it's the proton. So it balances out the charge of the electron if there's the same amount, and the mass is 1 H atom equals 1 AMU. And so that's the cool thing is that's really when, after 1920, when we started to have the periodic table set up in the way it is, with direct protons defining the elemental atomic number, because according to how many protons, because each one equals 1 AMU off the 1 hydrogen atom model, we're able to say, wow, 6 is this, 12 is this, according to how many protons it has. And so that kind of gets into our final slide, which is the modern view of the atom today. Here on the left, you have a gold atom, 288 picometers, minuscule, so tiny. But you see most of it is electron cloud and electron orbitals. And then very small in the middle is the nucleus, which is protons and neutrons, but it's most of the mass. And so interesting. That's where we came, that whole path. So I guess just in conclusion, like, and to make it to the 20 minutes, like, this concept is so simple. I think now we all are just like, okay, we got this. We got this. Why do we have to review it? But in my opinion, the reason why it's important to review this concept is because it really is the center of everything. If we don't understand what's going on or how an atom is made up, none of these other discoveries, none of these other things would have come to pass. And that's why we're able to predict how molecules react together, because of how many electrons they have and the orbitals they have. We're able to predict the weights of them. We're able to predict the speeds of them, the pressures they exude on other substances. We're able to predict even like how they travel through substances, how they just everything. It's really interesting. And so with that, like, that's the end of my little presentation, but it's interesting how atoms set up. Atoms rule the world. They're the center of everything.